Hi. How you feeling, baby? Need ice? You don't have ice, do you? You do? Okay.
Hello, everybody.
Greetings.
Good afternoon. we have one more homework remaining in the course. This is optional. It is due. Notice the time and in the same manner, quiz on Friday is optional. And it's due final exam. Regarding the quiz from last class, it was talking about how a valid answer, what happens to the angular speed when you increase or decrease the angular moment of inertia. So if you have a valid answer, so that's your hands. And your face, if you bring the hands closer, so hands closer means I decreases, moment of inertia decreases, I is mass times radius square. Since L has to remain the same, L is equal to I times omega. So if you decrease this, angular speed has to increase. So when you bring the hands closer, you start spinning faster around the axis which is passing through the body. Okay. Today we want to talk a little bit in detail on what we have been using all along, but we want to see the specifics and how it really applies in a cosmic scale. By cosmic scale, I mean when we don't talk about distances that are on the surface of Earth, 1 meter and 2 meter. Instead, we want to talk about huge distances, what happens to a satellite, which is relatively far away from the surface of Earth. And the masses that come into picture are significantly larger. Now we're talking about the whole mass of Earth, mass of Sun, and so on. So broadly, we will call this gravitation, which in a significantly simpler form we have been using all along. But we want to see it in its full form. Gravitation depends on a property called mass, and I should specify everything. So there are some fundamental properties of a, let's say if you were to keep breaking a given object into smaller and smaller pieces, and we all probably already know that eventually it becomes atom turns out to be one of the smallest block that is used to build things. But even an atom can be broken into a proton, a bunch of protons, bunch of neutrons and electrons. And it turns out electrons cannot be broken down further, but protons and neutrons can be broken further down. And in that way of looking at things, if we were to associate properties to these electrons and protons. For example, what really distinguishes these particles? And at that stage, the fundamental properties comes out to be, one is mass of the particle. For example, you can talk about what is the mass of an electron, what is the mass of a proton, what is the mass of a neutron, or for that matter, the mass of Earth as a whole, mass of us, mass of humans, mass of a car, and so on. So everything has a mass because the fundamental object that is used to build it has a mass. The second property, and one more thing, we use m to signify or denote mass, and it is typically larger than 0. It is never less than 0. Next is charge. Oops, I'm using the letter first. So charge. And charge is a second most important property that we come across. And you've probably already seen that an electron has a negative charge, a proton has a positive charge, and Q can be greater than or equal to R. So this could be plus infinity all the way and in principle minus infinity. So this is not equal, right? So this is plus infinity. There are about 4 or 5 properties one can list, but for now, let me stick to saying it also has a spin, and that's denoted by S. And unlike mass and charge, this is quantile, or this is discrete. So it can be 0, it can be half, this is 1, 3/2, and so on. So if you're not come across this, look it up. These are called fermions or bosons, so it's an important characteristic of a particle. Later, in the second part of this course, you will see what is a charge and what are the properties or what equations govern that. Spin comes later. For now, we are talking about mass. That's the important parameter we are using here. Anything that has a mass, almost everything that we see around us has a mass except photons. Right? So m equal to 0, there are objects that do not have a mass, and an example is photons, which are basically building blocks for light. Building, like the way we are built out of protons, neutrons, and electrons. So if you were to take light and break it up, block of light. It's hard to imagine, but when we study it in detail, it comes out that there is a property called photon, and its mass is 0. And there also is this property which is not really needed for us, is us here, is that if anything has a mass 0, then it inevitably has to travel with the speed of light. That it doesn't have a choice. It cannot be at rest. That's what it means. That's all little general knowledge for now. The only quantity we need is that everything has a mass, at least 0 mass or greater than 0. If it does not have any mass, then it will not participate in this in gravity as we know it for now. Later things change. So Newton's law of gravitation. This should be differentiated from Newton's laws of motion. This is Newton's law of gravitation. Tells us that if any two objects have masses m1 and m2, then each one of them experiences a force from the other mass, and this is the force F, let me say, onto by 1. So this should be read as on 2 by 1 on mass 2 by mass 1. And that's equal to, at least the magnitude wise, this is a constant g times m1 times m2 over the distance between them, the center to center. This could be huge masses, this could be the sun, this could be the earth, then there is a slight ambiguity there. Oh, what is how do we calculate distance? Always from the center to center. In fact, it is center of mass to center of mass. If there is a asymmetry in the distribution of masses, then you actually have to calculate the center of mass. If they are spherically symmetric, then the center to center is the correct way of saying. So that's your distance r there, and this depends on r square. That's your magnitude of the force that we want to talk about. That is the direction. We are talking about the force on 2 by 1. So that is a force acting at the center, the object, and that's your force on 2 by 1. Notice what's happening. 1 is attracting the 2, so it is intuitively clear that it will attract it towards itself. In fact, Newton's law tells us that it will point exactly towards the center of the mass 1. And that direction, so it doesn't have to be along the x-axis. That is a choice. I made it I drew the diagram in such a way that it is aligned with the x-axis. It could be rotated off. And whatever the direction is, that we will call as minus r hat. Because r itself could be, if with respect to 1, it could be increasing in that direction. That's the direction of r. So let's say this is the direction r hat. And force is in the inward direction, or if we think of r as a radially outward direction from mass. But that is all a choice. If I were to ask what is the force on 1 due to 2 because of the symmetry, that also has to be the same. That should be no asymmetry between the two masses. If they are identical masses, that we cannot differentiate between them. And you would say this is force on 1 by 2 will be exactly negative of F21. And all that is completely compatible with the Newton's laws of motion, which tells us that if one exerts a force F21 on M2, then there has to be an equal and opposite reaction force, and that's your reaction force. So all that works out well. But now we want to change this interpretation a little, and before that I should actually a small caution here. Notice I pointed out that a photon has mass m equal to 0, and in Newton's gravity, a photon will not get attracted to a mass. For example, if you have a very heavy object like sun, and if there was a light coming from a star very far away, that light is not going to be attracted by the sun. But that is the change that Einstein made to this equation, which we won't be able to capture. And that is that even photons which have 0 mass will actually get attracted by another mass. In this case, we are talking about a sun. But Newton's law cannot capture that in that sense. Newton's law is not completely exact. But having said that, when we are talking about planetary motion, if we are talking about motion of Pluto or Jupiter or Mercury around sun, we can use Newton's law to predict its position pretty much 1 second. That means to say a degree is broken into 60 minutes and 1 minute is broken into 60 seconds. Almost about a minute in 100 years. So where the position of Mercury is going to be in the sky, to very great accuracy, we can predict using Newton's laws of motion. Einstein's corrections are relevant in certain situations, but not necessarily everywhere. So most of the time, we are pretty well off with Newton's law of gravitation. And we will try to understand this in more detail here. So now we want to change this interpretation a little. So we are going to introduce, so this is the gravitational force. And now we are going to introduce, so maybe I should point out, so this is the gravitational force. I want to differentiate this a little or clarify this, and we have sort of used this all the way, but we did not emphasize this sufficiently. And here we want to write this as m2 times g1, and this notation is important here. Now what we are saying is that there is a gravitational field. Earlier we called this the acceleration due to gravity, which is indeed the case if that is the only force acting on it. But that's not going to be the case. In general, we would say there is a field generated by mass 1, and m2 experiences this field. So let me write this down first. So there's g1, which is equal to minus r hat. This is minus r hat, and that is g m1 over distance r squared. It seems like it's a trivial breakup. We have a mass m2 times g1, and I defined g1 as whatever was remaining. But what we are saying is that this already exists. This exists without the presence of m2. So let me clarify this. So let me call this the gravitational field. What is the difference in the definition? One is a force, and the second one is a field. So let's clarify this. So let me talk about a force. First of all, the language itself probably clarifies what it means. We say when we are talking about a force, we talk about force on mass 2 by mass 1. When we use that language, there is a meaning we associate to that we are exerting a force on another object by the first object. Here, notice the field is at, not on, at point. So there is no mass 2 to begin with. The at point, or maybe I should clarify, at a point. Okay, so at a point in space due to mass 1. That means to say that the moment I have m1, so independent of where m2 is, imagine a space or universe where there is only m1 sitting there. There is no concept of force. If there is only one mass, you cannot talk about force at all, because force by definition requires two objects. One exerts the force on the other. But unlike force, field exists everywhere in space. For example, here you have a gravitational field in this direction. Somewhere else here, it points in this direction. Somewhere closer, it will be much larger, so I will draw that using a much slightly longer vector. So that's towards the center of it. So it's towards the center. So that's your G again at that point, everywhere around. So if you're somewhere here, it's slightly weaker, it's smaller. That's in G. Everywhere G exists, and in that sense, if you were to think of G, you will think of it as the force a test mass, right? Force a mass would experience. So force a mass would experience. We don't have that mass. So this is a test mass, an imaginary mass if you want. If you were to place a unit mass there, that's the amount of force it will experience. So that's the change in interpretation. But the big conceptual leap is that this is physical. When we are talking about force, we don't talk about what is there in between the two masses. Currently, what we are saying is that the whole space is filled with an entity, which is the gravitational field, and G in space has energy associated with it and momentum associated with it. Okay. Even without the presence of M2, we can talk about energy that is filling per unit volume of space. Per unit volume, you can talk about a momentum. And those are the new concepts that will come in. And we will touch on these things very slightly. And first of all, mainly we will try to differentiate between force and a field. And similarly, we will talk about energy and potential. Again, the main criteria is that field does not depend on the second mass. So let's do an example to clarify. Oops. So example. Let's first talk about just one straight line. That is M1 sitting here. That is origin here, and that is M2 sitting on exactly distance D on the other side. So let's also say these are identical, no. So let me say this is 4 times M1. So M2 is 4 times M1. This is distance D apart, and that's also distance D. First, let's talk about that particular point alone, and I can talk about the force on M3. Right. But let me not put that, so that will act like my test charge. At this point, notice I don't have any charge to or any mass to begin with. So we will talk about gravitational field at point 1, sorry, due to point 1 at 0. Let's say this is origin, at origin, is equal to, if I were to, so how do I know the direction of the gravitational field at this point? You pretend that there is a mass here, and you ask in what direction is it going to experience the force. So it is going to experience a force, an attractive force due to M1. So that's minus I. So this is with respect to a direction, since everything I'm keeping along the horizontal line. So I is a convenient notation set. So minus I hat times G times M1 over D squared. That's my gravitational field at the origin due to the mass M1, and it is pointing in the negative I direction. That is another mass M2 on the other side that will also create a gravitational field. In fact, it creates gravitational field everywhere. With what is called the gravitational field, which has energy and momentum associated with it. At this point, how do we know the direction of G2? Pretend that is a positive mass there. it will get attracted to that. So that gives me the direction. So that's plus I hat and G times M2 now over distance d squared. It's the same distance I've chosen, so that remains the same. This is, since M2 is 4 times M1, so this is plus I hat minus 4 times G M1 over d squared. That's good, but what is the total gravitational field? This is the individual pieces that are contributing to that. So G at the origin would be, assuming that these are the only two masses contributing to the gravitational field there. In general, all the masses everywhere in the universe contributes to that, but many of them will be negligible because once they are very far away due to the inverse square dependence, even if you're very heavy, often the contribution is very small. So this is equal to G1 plus G2, which is equal to, if I were to add these two quantities, the second one dominates, keeping the distance the same, the masses are larger. So this is plus 3I hat times G M1 over d squared. Having got that, let me continue on to the next part. So what I have here is again drawing the same picture. So that's your origin O, that's M1, that's M2, which is 4 times M1. What we have calculated is the total gravitational field at the origin. So this is at origin is equal to plus 3 times I hat times G M1 over d squared. If I know the values for mass and the distance that we are calculating, we have a number there. And what would be the unit of gravitational field, since it is almost equal to the force except for a mass, so it will be Newton per meter. So units is, sorry, Newton per kg. So the units is Newton per kilogram. That's good, but we are usually interested in the force eventually, right? So what is the force on? So force on a mass M3 at the origin, if placed at the origin, would be, so F on 3. So let me just say this is just on 3 due to M1 and M2 is equal to M3 times G. So now we do not have to differentiate between how much contribution it is getting from M1 and how much it is getting from M2. So once you have this, you just multiply it by G. That's the straightforward relation. So that's plus 3I times G M1 M3 over d squared. But this is coming from two different terms, remember. So that's the point. But anyway, so our idea is that first you find the gravitational field, which has a physical meaning of its own, very much like we have properties associated with matter. This is a property that you can associate with space itself. Very much like a magnetic field, since we play around with magnets which are relatively stronger when they are in our hands. And magnetic field, if you feel like even without the second magnet, it has a presence in the space, like it can actually alter the quantities that are close by in it, even without the second magnet in it. So that's very similar property here. There we call it a magnetic field. Here we are calling it a gravitational field. And to see the effects of gravitational field around around objects which are heavy, or around objects, you have to have very heavy masses, typically of the size of a star, and so on. So that's the primary difference. Let's do a couple of more examples to differentiate these properties or bring out this difference more clearly. So the example we talked about earlier is a one-dimensional example. So now let's do an example which has directions coming in a slightly more complicated way. So let's say that is a mass m again. Let's say it is just let's say m1, and that is m2. But having said that, I say that's just a label. M1 is equal to M2, and let's call that just M. Let's say this is separated by a distance 2 times A from center to center. So that's A, that's another distance A. And we could talk about what is the gravitational force somewhere here. Not gravitational force, gravitational field, right? There is no mass there. So this is M1, that's M2. There is no mass there. So earlier we wouldn't have talked about what is the force acting at that point. And even now we don't talk about a force, but there is an idea of G at this point. At this point in space, there is nothing out there. We say that there is a gravitational field due to this mass M1. And what is that? Draw a line, straight line from that point to the center of mass M1. And if this was a positive mass, it will get attracted, and masses are always positive. So that's your G1. But there is a contribution from M2 also. So M2 will also attract a hypothetical mass that you would like to keep at that space point, and that will be in this direction, and that's your G2. Clearly, its directions are different, and because they are the same masses, actually their length will be the same, but in general, they don't have to be the same. So let's see what G1 is. So G1, for that I also need this distance, right? So that's my A, and I also need this distance. Let me call that Y. And I'm going to keep that as a variable so that then I can talk about what if I change my Y a little up or down, how does the gravitational force change due to that small change in the position of the mass. So G1 will be, as far as magnitude goes, that is G times it relates to only mass M1. So that's M1. And the distance square, the distance between the center of the mass M1 to the point of observation, where we are pretending we would like to keep another mass, or what is the gravitational field at that point, we will call it an observation point. How far is that? Since I know this is a right triangle, so it is a square plus y square. So that's a square plus y square. And it's already a square. It should have been a square. So using Pythagoras theorem, we know that that's a square plus y square. That's the magnitude, and I need a direction now. And the direction will be, this is whatever this direction is in this manner, but I can get the direction if I were to say this is angle theta. So let me write that as maybe r hat, so r1 hat, let's say. That tells me that that's the direction of the gravitational force G1. What is r1 hat? This is a unit vector. So how do I get r1 hat? I draw a unit line. So we have a triangle like this. That's my A, that's my Y, and I need to pretend that this is a unit line. So that will be my R hat. It is in the, if I were to think of this as my origin, that's in the third quadrant. So if I were to have this angle theta, I can actually get that direction of that vector. And I would say this is, this will be sine theta, right? So it is minus sine theta in the I hat direction. And the Y is also in the negative direction. So it's minus cosine theta in the J hat direction, where theta is given in terms of A and Y. So gravitational field due to 1 is given by a magnitude, which we already know. But now it has a direction because I need to add these two, G1 and G2, right? They're in arbitrary directions. So this is equal to minus sine theta is A over the hypotenuse, which is A squared plus Y squared in the I hat direction, and minus of Y over A squared plus Y squared in the J hat direction. That's fine. G1 and G2. Let me write that more explicitly here. So G1, combine these two relations. So this is G1 over A squared plus Y squared times this unit vector has a significant character in it because all this has to contribute in there. And then we have to talk about the same thing for M2 and they have to add up. So this is minus A over A squared plus Y squared, I hat direction, minus Y over A squared plus Y squared, and the J hat. That's your total force due to just the mass 1, not the force. I keep saying force, it is a field generated by mass 1 at the point of observation. G2 is very similar because we chose our problem in such a manner that there is a lot of symmetry in there. M1 is the same as M2, so this is GM2, which is exactly the same as M1. The magnitude remains the same, A squared plus Y squared, because this distance is also, this is also A here. It is A squared plus Y squared on the other side too. When it comes to direction, there is a small change. The X component is in the fourth quadrant, that becomes positive, but the Y component remains exactly the same and it is in the negative direction. So except for this plus sign, everything remains the same. And this stays minus. This can be visualized in a single step, and that's what we are going to see in a moment. If I were to do total gravitational field at the observation point that we are talking about, G1 plus G2. Notice if I have to add these two quantities, then these are exactly identical pieces. These two cancel out and I'm adding them. And it's only the J hat piece that contributes and it's in the negative direction and there are two of them. So there is negative, these are the negative pieces. There's -2 and there's a J hat and rest everything stays the same. So this is GM1 and then there is Y. And I can, when I write this down, there is a, if I write it as a square root of A squared plus Y squared, there's a half and a power of 1 here. That's 1 plus half is 3/2. So that's A squared plus Y squared raised to 3/2. Let's see that again. Notice that it is in the direction of g hat. So let's see how that is happening. So that is a g1 in this direction. That is g2 in that direction due to the two masses 1 and 2. But what's happening is that as a vector, this can be broken into an x component here, an x component from the first vector, and the y component from the first vector, and the y component from the second vector. Since they're identical masses, the x component cancel out. They are in the opposite direction, so they cancel out. But the y components add up. So effectively, there is a single force acting in the downward direction, and that's in the y direction. But now its magnitude is not given by 1 over r squared, because there is an angular or the component contribution that is coming in. That is a length of this vector that has to be projected in the y direction. So the power goes by y over a square over I square. There's an extra piece, which is basically the cosine theta expression that's coming in. So expression is now given in terms of raised to 3 by 2. So if I collect that in here, so we have, oops, change. So we have the observation point there, mass m1, mass m2. Effectively, the gravitational field is acting towards the center. That is a G1, G2, but all that effectively is giving you a gravitational field, acting downwards along the y-axis, and that's equal to minus 2j hat. 2 can be written that way also. So that's g times, I said m1 is equal to m2, so that's g times m, and then there is y over a square plus y square raised to 3 by 2. So that's a gravitational field. That means to say how much if mass, a third mass m, will experience, that will come and sit in here, right? You have to multiply that. Mass m would experience if you were to place it at this point. So force on a mass 3, let's say, would be equal to m3 times the gravitational field. So this is F3, so mass will be m3 times g. So that will be the interpretation. Again, going back with our understanding, force remains mass times the gravitational field, but the gravitational field itself has a physical meaning in this case. Let's do a small analysis here. One could ask, when is the gravitational field the maximum? Right? You could, what if I were to plot this? So if we were to going from here to there, at what point is the gravitational force going to be a maximum, which will be decided by at what point is the gravitational field a maximum along that line, and that means for what y is it going to be the same? And immediately you would say, oh, you want it to be very close to 1 and 2, but there is this feature that if you're right at the center, the component of y is not contributing, so it is 0. So intuitively, the immediate intuition is that, oh, it should be closer, right? So it should be here, but at this point, this is 0. There is no force, right? So forces are in opposite direction. There is no component in the y direction. There is no gravitational field there. So let's ask the question, at what height y is g, the magnitude of g, a maximum or a minimum, right? A maximum or a minimum. Should there be a maximum or a minimum? So let's again find out what happens. So if I were to plot this, as a function of y. So this is the magnitude of the gravitational field. That again, gravitational field is the force a third charge would experience if you were to place it at a certain point y along the line connecting them. So what is the, oops, I think I need the expression. Yeah. If it was right at the center, that means y is equal to 0. You notice that, oh, y is equal to 0 in the numerator. In the denominator, the a is not 0. So it is right at 0, it will be 0. So it begins from 0 in here. And as you grow a little, it actually grows a bit. So at y equal to 0, it's somewhere around there. What about y tends to infinity? When y is very large, well, that means you're very far away from these two masses at that time. So y is very large, so a is really small compared to y. So this can be neglected, and I would say it is y over y cubed, right? So that's y over y square over 3 by 2. So that's approximately y over y cubed. So that's 1 over y square. Right? So when y is very large, the gravitational field decreases by 1 over y square, which makes sense because very far away, these two masses look like a single mass. And we know that gravitational field goes down by y square, but it anyway goes to 0. Right? So it goes to 0 here also. That means to say that you grow here and you come down here, so there must be some maximum value here, right? So probably this goes like this, maybe. If you were to plot this, it is somewhere like this, and then immediately you ask, oh, but what point? Well, there's some special point here when, let's call that y naught, right? And when the force is at, or the field, gravitational field at that point is a maximum, and that whenever there is a maxima or a minima like this, a plot, it's always nice to ask, what is that point? And we have done this before, these kind of examples. We take the derivative of this expression to be and set it to 0. So let's do derivative with respect to y now of the actual function is y over a square plus y square raised to 3/2. That is a constant in fact, and the gravitational field is given by that, but pretty much that's given by that quantity. This gives you y is just 1 over a square plus y square. That's the derivative of the numerator. And then keep the numerator the same and take the derivative of the denominator. That gives me a minus 3/2. Then I take the derivative of the denominator. It changes the power to 5/2. Like 3 by 2 becomes minus 3 by 2 when it goes to the numerator. Then subtract 1. Then you bring it back to the denominator, it becomes 5/2. And then take the derivative of the argument of a square plus y square, which is 2 times y. That's your derivative. I have to set this to 0, so it's only the numerator that matters. So I have to make this common, so factor 2 cancels out. So I have a square plus y square and minus 3y square divided by a square plus y square raised to 5/2. If I want to set this to 0, why am I setting this to 0? Because the slope has to be 0 right at that point. So whenever I set y naught equal to 0, it's a numerator that is important. So that's, or let me write one more step, right? A square minus 2y square over a square plus y square. When is it 0? Whenever the numerator is equal to 0, and at that particular point it is y naught. So this is 2 times y naught square has to be equal to 0. That's that point here. Whenever y is equal to y naught, the numerator has to go to 0. That means y naught is equal to plus or minus a over root 2. Plus or minus means that there is a point above and below those 2 points, and plus or minus 1 over root 2 will be slightly less than A, right? So if this was distance A, somewhere here is what, so maybe the diagram would be, so that's your two masses. And if this was the equidistant, so that's A, and that's also a scale there, there's an A there. And if you were slightly less than, so at this point somewhere there, you will have a point where the gravitational field is a maxima. That means its components are what is deciding what your force is there, or there is a one action is that the component has to be sufficient, and the second is that the force itself should be sufficient, and there is a give and take between them, and at this point it comes out to be the maximum. I'll stop here, and next time we will talk about energy, gravitational energy, and the associated quantity, which will be called the gravitational potential. I'll stop here, and thank you.
Have a good night.
You too, Blake. Any more questions?